KrisOS is an embedded operating system for an ARM-based microcontroller with real-time capabilities. It was developed as part of the third-year project module in the School of Computer Science at the University of Manchester. Before I demonstrate my achievements, I believe it is necessary to introduce the concept of real-time applications and explain how the operating systems have been adapted to serve these applications. Anti-lock braking systems, thermostats, and flight management systems are all examples of real-time systems. They must respond to critical events within a strictly defined time. Severe consequences are unavoidable if logical as well as timing correctness properties of the system are not met. Real-time systems can be classified into two categories: hard and soft. Hard real-time systems are used when it is imperative that an event is reacted to within a strict deadline. Missing the deadline results in a total system failure, possibly damaging the surroundings or threatening human lives. For soft real-time systems, the usefulness of the result degrades after its deadline. Even when the timing constraints are violated, they can continue to operate with impaired quality and recover in the future. Consequently, a group of operating systems called RTOS, which stands for Real-Time Operating Systems, has emerged. They forsake many of the functions of the commonly known desktop OSs in exchange for compactness and efficiency of resource usage. This means that the device drivers need to be supplied with the user code. RTOSs require a certain level of expertise from their users. Therefore, they are designed without excessive protection mechanism for qualified embedded programmers. Contrary to desktop OSs, the application code is statically linked into a single executable file together with the OS. The same design principles were applied to KrisOS, which aspires to be an RTOS. Now, let's have a look at my OS implementation. KrisOS features a priority preemptive kernel augmented with round-robin scheduling. Among the inter-task communication and synchronization objects supported are mutual exclusion locks, semaphores, and queues. The priority inversion problem, so disastrous to real-time systems, is countered using the priority inheritance protocol. The OS User Statistics task is a tool which aids application debugging by giving a useful insight into the internal OS operation. Lastly, KrisOS incorporates an optional heap manager. The project was developed for the TVASI Launchpad Evaluation Board from Texas Instruments, with an ARM Cortex-M4F based microcontroller unit. KrisOS is fairly simple to use. First, the operating system has to be initialized. After this stage, the scheduler is ready to register user-defined tasks. These can be created both statically or using heap memory. Regardless of the type of memory allocation used, a few task-describing parameters have to be passed. In order to speed up the variable declaration and initialization process, precompiler macros are used. Each task is implemented as a void method, which takes no input arguments. Two types of tasks can be distinguished. The periodic tasks never return. They consist of the setup stage executed once and the main body enclosed in an infinite loop. Conversely, the one-shot tasks are automatically removed upon completion. KrisOS requires only a single header file to be included in the application code. It acts both as a configuration file and interface specification. Various optional OS features can be switched on and off. In addition to this, settings like heap memory size or scheduler time slice length can be controlled. I believe that the best way to demonstrate the capabilities of my software artifact is via user applications, which, by requesting various KrisOS services, show the full spectrum of the OS functionality available. The first demo consists of 4 tasks. 2 of them are created by the user, while the remaining ones are maintained by the OS. With multiple tasks trying to produce text output via the UART module, a single shared resource, the contention problem arises. In accordance with the task priority arrangement, each task can write to the output stream as soon as it grasps the processing unit. This causes the text displayed on the serial monitor on the right-hand side of the screen to be mixed up. Furthermore, the usefulness of the OS User Statistics task can be appreciated. It allows continuous tracking of, for example, the heap usage or the per task processing time and stack usage. Notice how the prime number task got automatically removed from the scheduler upon completion, and the dynamic memory it occupied has been freed. The resource contention problem can be resolved using a mutual exclusion lock offered by KrisOS, which ensures exclusive access to the UART module. By enabling this feature, even more debug information can be learned from the usage statistics task. The second demo shows a real-life interactive KrisOS application. In addition to the periodic threads, such as the RGB LED color changer or the thermometer, a couple of event-driven tasks are also present. The latter are relayed using semaphores inside interrupt service routines, once the trigger condition is met. This time, various external modules are interfaced, often using popular serial communication protocols like I2C or SPI. These peripherals include a temperature sensor, photoresistor, piezo buzzer, LCD screen, button switch, and the light-emitting diode mentioned earlier. Two of the tasks are also exchanging data between each other using an OS implementation of a queue. KrisOS achieves concurrency while maximizing responsiveness. In this demo, the gradual change of the LED color in the background seems undisrupted by temperature changes or varying light conditions. At the same time, there is no observable response latency to external events. Thanks to the operating system, a reasonably complex embedded application was broken down into a set of manageable execution threads. The demo applications show that KrisOS is operational. However, they do not give any qualitative figure regarding the OS performance. Usually, the hardware running an RTOS has limited RAM and ROM. My software tackles this issue by offering a scalable memory footprint. Redundant features can be disabled to save resources. As a result, KrisOS boasts 8.6 KB and 1.69 KB of ROM and RAM usage respectively, with maximum configuration. The OS response latency was also measured using an oscilloscope, and it is equal to 350 clock cycles on average. Thank you for watching.